Hi, I'm Maddie Stone, and this is the state of 0-day in the wild exploitation. What do you think of when I say 0-day exploits? It likely evokes images of only the few most elite hackers around the globe, targeting only the most wanted targets. You might think that these 0 days cost so much, are so hard, take so much time to develop, that only a couple of entities have the knowledge and resources to develop them. For the last 18 months, I've studied 0 days exploited in the wild. Not the theoretical or the hypothetical, but the ones actually being used against users. As 2020 came to a close, I began looking back over all of the 0 days we saw in 2020 and started putting together my second year in review analysis. This is not analyzing each individual exploit, but instead taking all of those individual analyses together to figure out what are the trends, what are the gaps, what lessons can we learn from the preceding year to then inform what work we do in 2021 to make 0-day harder. It became pretty clear while doing this analysis that we, as a tech and security industry, aren't requiring the most elite skills for attackers to be able to exploit 0 days. But thankfully, the analysis also showed that there is low-hanging fruit that can be implemented to directly and immediately make it harder to exploit 0 days. So let's get to it. First, let's make sure we're all working from the same definition. What is a 0-day exploit? It is an exploit targeting a vulnerability that defenders don't yet know about. So there's no patch available. There's not mitigations to say block this specific exploit. There's not detection signatures for your antivirus to alert you about it. Defenders don't yet know, only the attackers know. And so my work has been with Google Project Zero to learn from 0 days exploit in the wild, specifically to make it harder to exploit 0 days. So grounding our work in understanding what are attackers actually doing rather than what do we think they're doing. And so that's where all of this work in this presentation comes from. And that's why I write a year in review. So this presentation is a very quick deep dive into what I think is the most notable thing we can take away from 0 days exploited in 2020 and what do we do about it. So I'll show you a few different case studies showing you how that sort of thesis is backed up by data. Yeah, so let's get into it. From the most basic first start, there were 24 0 days exploited, 24 0-day exploits detected in the wild in 2020. So that's our base level. These are the 24 exploits that are informing this analysis. And as I was working through each of them, looking at them all together as a group, the number that stuck out the most to me was that 6 out of the 24 0 days exploited in 2020 are variants of previously disclosed vulnerabilities. They are variants of vulnerabilities that have been reported before, published about before, seen before in previous exploits, etc. So said in another way, 25% of 0 days from 2020 are variants of previously disclosed vulnerabilities. They are similar, only a few lines changed in some places, to vulnerabilities and exploits that the industry public knowledge knows about. On top of that, 3 out of the 24 vulnerabilities were incompletely patched, meaning that with just a few tweaks, you could have an exploit that still works even after the patch was applied. So through all of this, it became pretty clear to me that what I can take away from 2020 and the 0 days that we saw is that across the industry, incomplete patches are making it easier for attackers to exploit users with 0 days. We are not requiring attackers to come up with, all new bug classes, develop brand new exploitation, look at code that has never been researched before. We're allowing the reuse of lots of different vulnerabilities that we previously knew about. So let's get into my 3 case studies. This first one is Internet Explorer Jscript. So Jscript is the legacy JavaScript engine included in Internet Explorer. While it's legacy, it is still a great attack vector because it is enabled by default on current Windows machines. So through a quick timeline of, this saga, this case study, This bug class that we're going to be talking about was publicly discovered by a researcher in January 2018. And through that, numerous vulnerabilities were reported to Microsoft. In December 2018, the first detected case of a bug in one of these bug classes being exploited in the wild was discovered. In September 2019, another vulnerability in this bug class was exploited in the wild. In November 2019, another patch had to be issued because the patch in September didn't actually fix the vulnerability. The exploit and the proof of concept still worked even after that patch had been applied. The November 2019 patch also fixed a trivial variant that hadn't been patched previously. In January 2020, another trivial variant of the vulnerability exploited in September, CVE 2019-1367, was exploited. And then in April of 2020, another variant within this bug class was patched again. And I think one of the things that also sort of hits home the importance of these correct and comprehensive patches and how we need to be patching, the variants and not just the single bug, is that the same attacker exploited all 4 of these vulnerabilities, according to Google's threat analysis group, who published about this back in 2020. So that attacker had 4 different chances to use these 0 days to exploit users. And now I'm going to show you just how close each of these vulnerabilities were. To trigger them, usually only 1 or 2 lines of code had to be changed. So we're going to start with the trigger, the proof of concept for 2019-1367, the vulnerability that was exploited in the wild in September 2019. So this vulnerability specifically, and this bug class as a whole, so first the bug class. The bug class is that a Jscript object is not tracked by the garbage collector, which leads to a use after free. And so in this specific case, the arguments array is not tracked by the garbage collector in the array.sort callback. So in this sample right here, this is where we're calling array.sort. We're using function f as our callback. So when that's called, we're going to execute function f. In function f, first we have to create a whole bunch of these Jscript objects. Then we're going to assign one of them. We're going to give arguments array one of the references to it. And so the arguments array, again, is the thing that's not tracked by the garbage collector. Then we're going to delete all of those objects and call garbage collection. So now that object that the arguments array has a reference to has been deleted. And so that's what leads to our use after free. So then 2 months later, as I said, Microsoft had to issue another patch. The first part of that was they actually fixed CVE 2019-1367 this time. But the other is they also had to go in and fix another trivial variant. So this variant, to trigger that vulnerability, you only need to delete 1 line of code from the previous POC and add 2. POC meaning proof of concept. And so in this case, it's not the array.sort callback that is not being correct. The arguments array is not tracked correctly in. It's this time in the toJSON callback. So we simply replace the sort call to JSON, and then we can trigger the vulnerability again. Then that wasn't the end, as I said, because in January 2020, another trivial variant was exploited in the wild. And this time, it's not the arguments array, it's a named argument. And so what that looks like is, again, we have our 1367 trigger right here. And the keys differences were that in this case, we define the function with no arguments, and then we use the arguments array to store the reference to the object that will be deleted. For 2020-0674, the vulnerability that was exploited in the wild in January, we instead put 2 named arguments in the function's definition, so arg1 and arg2 in this case, and we just replace any place that we have arguments 0, the arguments array, with arg1. So those were the only changes needed, and you had another 0 day. Yeah, so we're showing it's not hard. Once you understand a single one of those bugs, you could then, just change a few lines and continue to have working 0 days, find the other ones that hadn't been patched and were missed. This case study in Chrome is going to be a little bit different. Instead of talking about the variants, I'm going to show you an example of incomplete patching, meaning the root vulnerability wasn't fixed the first time around. And this is a kind of an interesting use case because when this vulnerability was patched, it wasn't actually known that it was exploited in the wild. That came 2 months later that it was found that it had been likely exploited as a 0-day. And so it shows the importance of patching completely all vulnerabilities because we know we have a detection gap. We know we're not detecting every 0-day that's exploited. If you want more about that, check out my year in review from 2019, which is linked in the references. But yeah, I think it's a pretty understandable thing. We don't detect them all, and so we need to be fixing everything as if they are. So in this case, it is a type confusion in Chrome's V8 JavaScript engine. So here's the general timeline. In November 2019, a set of security researchers reported the vulnerability. This was a bug collision, likely with the attackers who are using it as a 0-day. And we say that because the proof of concepts, the way the report was written by the researchers was very different than how the exploit was written. And so in February 2020, Sergey from Project Zero, our team, discovered exploits using this vulnerability and that it was likely a 0-day and that, so it had likely been in use prior to November. Because of this importance, he decided to do a patch analysis from where the vulnerability was reported by researchers. And what he found was that it was not a correct and complete patch. It had patched one way that this vulnerability could be triggered, but it didn't patch the other ways. And so so Chrome went and very quickly released another patch, this time as CVE 2026-383, but it introduced a new issue, a new vulnerability that patched it, which Sergey again recognized, and a new patch was then released for it. So we're going to talk about the first incomplete patch here. So this is the trigger for the original vulnerability. So the vulnerability is in, as I said, Chrome's V8 JavaScript engine, and it comes about as a type confusion. So in this case, within for loops, there is an area where it is going to try and do some induction. The key is that the V8 type of integer kind of has a special type because it's not only including numbers, but it also includes negative infinity and positive infinity. But the other aspect of this integer type is there is no guarantee that when you add two integers together, it's going to give you an integer. Instead, negative infinity plus positive infinity, for example, will result in NaN, not a number, which is not a member of the integer type class. So that's this vulnerability, is that in this for loop, we are able to cause a sum to be not a number, aka not an integer, and that case wasn't being handled correctly in the V8 engine. So what it looks like, we have our for loop here. The original index is going to be negative infinity. And then our increment, which was assigned in the line above, is positive infinity. So when these are added together, it equals not a number, which was not handled and led to this vulnerability. So they patched that, they covered that if, your original index is negative infinity and the increment is, positive or vice versa, then we're not going to go down that code path and handle it differently, thus preventing the vulnerability in place. However, they did not cover the case where you can actually change the increment within the for loop body, thus triggering the vulnerability again. So for CVE 2026-383, the second patch, this was the trigger, is again, we have our for loop, but the original index this time is 0, while the increment is negative infinity. That's just fine because 0 plus negative infinity equals negative infinity, which is still an integer. However, what we see in this POC is that once we go through it once and I is now negative infinity, we change the increment to positive infinity. So when we do that, now we're going to have the next time through the loop, negative infinity plus positive infinity, which then is the same triggering, triggers the vulnerability, again, just in a different way this time because it equals not a number. And so that's where we really need to make sure that all patches are not just patching to whatever proof of concept or whatever exploit you see, that we're really getting down to what is the root cause vulnerability and how do we patch that correctly and completely to make sure there aren't other avenues to still trigger the same thing. Our last example and case study to sort of show you about, this trend is an arbitrary pointer dereference in the SPL WOW64 DLL in Windows. So the SPL WOW64 DLL is used for whenever a 32-bit process and wants to print. The kicker is that SPL WOW64 runs as medium integrity, and Internet Explorer, which is a common 32-bit process, runs as low integrity. So this arbitrary pointer dereference was a privilege escalation. So the timeline on this one, July 2019, it's detected that a vulnerability, an exploit is exploiting this vulnerability in the wild. In June 2020, a trivial variant was discovered exploiting the wild. And then when doing patch and variant analysis, I found that that patch wasn't complete and it was still exploitable. And so then that was patched in January 2021. The reason there's two CVEs there is that they had originally been planning to patch in 2020. They missed the deadline and it had to go over to 2021. And so a different CVE was then issued. So what's the problem? Internet Explorer is able to communicate with SPL WOW by sending LPC messages. One of those LPC messages can trigger this code path in GDI printer thunk, which will then process that message. So the vulnerability in July 2019, it was the message type hex 75. And then the attacker can control in those messages, it would use different pieces to control all three arguments to a mem copy. So the destination, source, and copy size, but in the SPL WOW's medium integrity process. So you have this privilege escalation where low integrity Internet Explorer can read and write in the medium, aka higher integrity SPL WOW. This code snippet and a great write-up is by ByteRaptor, so I included the URL here. So I jumped ahead. So message send is all of the user controlled information from Internet Explorer, and we control destination, source, and the size. So in July 2020, 986, this time the difference was that it just wasn't the message type 75, it was instead hex 6D, and you had the same capabilities. The offsets of where each of the source, destination, and size for the mem copy were slightly different, but still same vulnerability, control all three arguments in a mem copy from the medium integrity process. Finally, their fix for that was to simply change the raw pointers to offsets, which still didn't break it. Just now as the attacker, instead of sending the raw pointer for the addresses you wanted to happen, you send offsets and calculate that to have control over their pointers. So that was not a fix. And then, so that was what was patched in January of this year, 2021. So hopefully I've shown to you that we have a problem. We're not making 0-day harder. It's or hard to begin with because you don't require all these elite skills. You don't have to be able to find new vulnerabilities to be able to exploit these 0 days. So what do we do about it? Thankfully, we have options. First, we need correct and comprehensive patches for all vulnerabilities from our vendors. We can't be leaving things open once they're known about. We need to use the information to do variant analysis to patch all of this instances of that vulnerability in the code base, not just that single one. So thankfully, each of us, depending on our role, all have opportunities though to help achieve this goal. As researchers, we analyze bugs for the patches, or we analyze patches for the bugs that we report and others report to make sure they're complete and correct. We do perform variant analysis. We brainstorm mitigation strategies. We offer to work with vendors and on patches before they're released to make sure we don't see holes already in their plan. And through disclosure policies or any other tools at our disposal, we can work to try and incentivize vendors for complete and comprehensive patches. As a vendor, it's a lot of the things I was saying that hopefully, researchers can contribute to by doing all these things and then reporting to vendors. But vendors, we really need y'all doing this internal to your teams too, of making sure those patches are not just breaking a proof of concept. And that's what we're seeing a lot of, is because there's a lot of ways oftentimes to reach a vulnerability. So making sure that root vulnerability is fixed rather than just one path to it. Also, reach out to us researchers. We want to help and make sure the patch is correct and is actually fixing the issue. We do this work, to help make things stronger and more defensive. So please use us. We want it, just the same as you, is for these patches to be correct. And lastly, as users, there are still things we can do too. We can hold our vendors accountable, call up customer service lines when it's out that they haven't issued a patch yet for something that's being exploited, or there's been news headlines or we learned that a patch wasn't correct, that we hold them accountable that, hey, if I'm going to use your software in your product, I need you to take security seriously and make sure these patches are working off of all of the different security holes that reports tell us about. And so that all comes back to, I'll use the phrase one more time, we need correct and comprehensive patches for all vulnerabilities to make it harder for users to be exploited with 0 days. And that's important. And I specifically say all vulnerabilities because we do know that not every 0 day is detected. So if we adopt this behavior for every single vulnerability that is found or reported to us, then we can definitely make it harder for attackers to use 0 day exploits. And lastly, hopefully in this quick 20 minutes, I've made you more interested in all this type of 0 day in the wild work. Couldn't include everything I wanted to clearly. So here's a whole bunch of great references, or I say great, I wrote them, so that's kind of weird. I hope good references. And with that, thank you for joining me. I really appreciate it. I'm Maddie Stone on Twitter, or you can reach us at Google and Project Zero doing this work at 0dayinthewild@google.com. Thank you so much.